I'm going to talk about 8 data science learnings from my business at Intuit, or our work at Intuit, where I'm in the payments processing division. I do, me and my team do the risk modeling and fraud detection, risk and fraud detection. I'm going to focus probably more on fraud than other kinds of risk. And I'm really going to want to focus on the 8 data science learnings because I want it applicable to everybody. So it's less about, what's particular in my business, what we do, although I'm open to questions about that, but more about kind of more generalizable lessons that we've learned and that can hopefully be useful to others. So we are, Intuit does a lot of things. You might have heard of TurboTax. QuickBooks is another product. We're in the QuickBooks ecosystem. So Intuit, besides the other things it does, is a large payment processor focusing on medium and small businesses, and we're one of the larger processors for medium and small businesses. Same kind of somewhat similar customer base to places like Square, PayPal, and so on. We have a special focus now. We do payments in lots of ways for lots of things, but our particular kind of strategic focus is within that QuickBooks ecosystem. We could process payments in QuickBooks, and that's what that graphic is showing you, is the ways things work in QuickBooks. So somebody can send an invoice in QuickBooks and receive payment within QuickBooks, and we facilitate that. We also facilitate mobile payments and all kinds of other stuff. And that's card and ACH payments or check payments. So there's a few types of risk we deal with. As I said, my team creates the models. We assess risk. There's a lot of other teams involved in the kinds of things we do that help us to get the things done we need to. And so they've also been involved in the things I'm going to discuss. So we have fraud risk. That can take many forms. It could be somebody saying they're a merchant that they're going to process with us, but really that they have no intention of doing legitimate transactions. They're not really a merchant. They're just trying to take stolen cards and get money out of them. There could be an account takeover where somebody takes over an existing account and tries to get money that way, but the original merchant's legitimate. There's other things that can go on as well. There's actually a lot of varieties of fraud. Financial risk in, for example, card payments is when a merchant, again, we deal with a lot of small businesses, there's a lot of risk of failure. If a merchant goes under and they have, let's say they've received a bunch of payments and they haven't delivered their goods, we're responsible for that if the merchant can't pay it. So the customers will charge back. So if you dispute a transaction and a credit card becomes a chargeback, and then the merchant's not there to pay the chargebacks, they didn't deliver the services, we're on the hook for that. So there's financial risk we take as well. As somebody who moves money, there's also a lot of compliance issues, and one of them is money laundering. We have a model for money laundering as well. Now, I'm going to take you through kind of where we've been in the last 5 years. And we started 5 years ago in our risk systems really being a pretty manual shop where we had a large number of manual cases. About 5 years ago, this was before I got here, we moved to hundreds of automated rules. So instead of creating as many manual cases, we had rules that differentiated risk and screened it. About where I came in and my team and I built some models that enhanced the rules. So we moved initially to just rules plus models, and some things were triggered by the models we created, and some things were triggered by rules. And then we moved beyond that now to what I call, and I'm going to explain what I mean by this, an ecosystem. of models, multi-level models. So it's an ecosystem of models within models. So we have meta variables, which can be models themselves. And by the way, I keep on using the word variables. I guess I'm a little old school, but you could think of them as features, signals, whatever you want. But so we have this ecosystem of meta variables, which is our risk models, and the rules are now really, they're ultimately what decides what to do with a merchant, whether to create a manual case or take some automatic action, is a rule, but the risk assessment is pretty much, with a few exceptions, all done by the models. So the models assess the various types of risk, and then the rules basically say, oh, this is a large transaction and it's above this risk level or something like that, and it says to trigger a case. So we've learned a lot of things along the way, and some are specifically about risk management and payments, but the things I want to focus on are the things that are kind of more general, and mostly it's related to predictive modeling, data science. There's been a lot of talks about kind of architecture, design of systems. I'm going to really focus on kind of the modeling and how we do that and what we've learned about that. Okay, so here's the 8 lessons that I'm going to go into, and here's the kind of just a quick run through of them. Varied data approaches to triangulate on truth. Everything is not a nail. Diversity matters. Flexibility matters. Automate what you can. Be wary of black boxes. Settle for 80% of value. And know what delights your customers and deliver. And so I'm going to take you through each of those. And by the way, it's a small enough group that if you want to interrupt me during the presentation and ask questions, and feel free to do so. We don't have to wait till the end if you have something you want to discuss or ask. So the first one, varied data approaches to triangulate on truth. What I've found is that the best way to get to the answer and to get at truth is to look at the data from several approaches in several directions. I actually read something recently that said most of the data, like 90% of data should be chosen strategically, that you should start from this kind of top-down and strategic approach, and that's what you should do 90% of the time. I'm not really with that. I think there's a lot of ways to get at truth, and part of it, yes, strategic data choices are very important, and what I mean by that is you decide what you want, you go find it, you bring it in, and so you're starting with, we need this, and this is predictive of fraud, and you go and find it, whether you have it or not. Bottom up is something that I think is really important. And by the way, it's the smallest circle, but that's really actually because of it's not necessarily the smallest. It's supposed to be the smallest group. It's really the sizes really vary depending on the task and the environment you're in and what you have. But what I mean by bottom up is there's usually some forms of boots on the ground people. For us, it's risk investigators, underwriters, people like that. People have actual contact and actually see what's going on. They have a huge amount of insight and huge amount of value, and they could tell you lots of things. And on an ongoing basis, they could tell you new things that are going on. It doesn't have to be, just for risk. If you're doing attrition modeling, it could be, the customer service reps who talk to customers. If you're doing marketing-related tasks, it could be, the sales people and other people who have closer contact with the customer, closer contact with what's going on, and that can be really, really valuable. The third is data exploration. Use what's already there. I think it's really important to just take advantage of what you have. And I would say for us, we still haven't fully taken advantage of what's just sitting there. And the advantage of that is it's already there. And I'm against just over mining and just throwing everything in. But definitely, when you look and see what kind of data is available to you, sometimes if you have good data available to you, you could come up with ideas and see things. Hey, I wonder if that is a useful piece of information that might give me insight here. So I think it's best to approach things from all angles. And we found a lot of value in all these directions. Everything is not a nail. What I mean by that is there's an expression that, when all you have is a hammer, everything looks like a nail. And what I mean is, don't just rely on one tool, right? Everything is not a nail, and you should use the right tool for the right job, and so you need to use different tools to approach different problems. I'm going to give you an example of what I'm talking about here, of what we've done. But I've found, like, for example, fraud is a very big problem, very big, lots of ways you could look at it, lots of people, lots of companies doing different approaches to find fraud for you, and we do ourselves lots of different approaches. I found it best to take a really big problem, split into sub-problems, and then match the solution to the sub-problem. So, and that's where the everything is not a nail comes in. You match the solution to the sub-problem and its nature. Well, I'm going to explain that in a second. So flash fraud is an example of a model we put in place, and that's exactly what I want to talk to you about. So we have a kind of our traditional fraud model is built on kind of looking at the long-term patterns in fraud. But by flash fraud, I mean a sudden burst of fraud. We get hit by fraud rings. So it's the same group of people, let's say, setting up, they could do various things. They could do account takeover, for example, or they could set up a bunch of fake accounts. But it's one ring coming at us at one time, trying to exploit vulnerabilities. So flash fraud is a sudden burst of fraud from a single ring. And as I said, the original fraud model kind of is focused more on long-term trends, but these specific rings have specific things that they do. And so when I think about what we see with the kind of the long-term things associated with fraud and these kind of short-term fraud rings and what we see there, I kind of separate the world into tendencies and patterns. And what I mean by a tendency is kind of these long-term things that tend to be true about fraud. While a pattern is something very specific associated with a specific ring going on at a particular point in time. So the timing for, as I described it, the timing for tendencies tends to be longer term. Of course, fraud's always evolving. Our products and everybody's products are evolving, and payments industry where I am is evolving. So it will change, but not that quickly. The patterns of these fraud rings are very quick. If you're doing your job, they'll stick around as long as you don't find them. But if you're doing your job and you find them, they'll be very quick, and as soon as they can't get money from you anymore, they'll leave, and then there'll be another pattern that comes along from another ring. There tends to be differences in the way features tend to work for them. So for our kind of long-term fraud, the tendencies, it isn't perfectly additive, but it tends to be kind of additive across variables, where if risk factor A is high and risk factor B is high, some multiplicative or additive combination of the two is how risky it is. Not true for patterns. And it tends to be directionally consistent across a single variable. And I don't mean that, again, generally just across every number, but like, for example, the amount of a transaction, there'll be a broad range where, let's say, higher transaction amounts is associated with higher fraud risk. Eventually, it kind of goes the opposite way, but it's kind of a broad range where it's directionally true. Not linearly, but directionally at least. While a pattern, you're kind of looking for an interaction effect. There's a really interaction effect dominated, and there'll be a sweet spot. So for example, it'll be factor A. You can't add to factor A, B, and C, risk factor A, B, and C, these features, because it'll be about the combination of them taking place all at once. And then in terms of the sweet spot, like using the amount example, it won't be like the amount risk goes up with amount. It'll be, let's say, this ring is doing transactions between $2,500 and $2,700, and that's the transaction size they're doing. So, they tend to have very specific things they do. So examples of a tendency would be like a free email account could be riskier, like a Gmail or a Hotmail or Yahoo. with a pattern, it'd be a specific set of things, like doctors with Gmail accounts from San Diego with a specific browser type. All those things at once are what we're being hit with. It'll be a ring. So, the bottom line, the reason I'm pointing out all this is because you want different tools. I mean, you want different model types, different time frames to look at both of those. For the tendencies, you can use a traditional statistical model. You can use a machine learning algorithm, but you might end up with a different machine learning algorithm. For the patterns, you want something that's very specific that targets interaction effects. You really want to be interaction effect, some kind of model that really can find complex combinations of things and patterns. So a pattern-focused algorithm, decision trees are good at it, neural nets are good at it, so those kind of things will work well. And the other key thing about it is it's very short term. So you want very short term, very rapid retraining. I'm going to talk about later how I don't really like black boxes, but for our flash fraud, we basically are using something where we're not looking at the results and we're retraining daily because the timing is so important of having something constantly updated and having it retrained to look at new patterns. So we're letting that run and looking at kind of what happens in the long term.
The flash fraud that you're talking about,
Yeah.
Can that be derived from previous fraud with one dimension being changed or few dimensions being changed versus totally new in terms of flash?
Yeah.
It just occurs in the same group.
Yeah.
And there
the
history is there and so on.
Yeah.
Are they changing only one or two parameters? Are they completely changing?
You know what? I think it's an interesting question. I've seen both. So sometimes they'll figure out. They'll be measure and countermeasure, and they'll figure out, we think they're looking for this, and they'll get rid of that and change that. And then you could use other characteristics. The nice thing about this model is it's changing daily, and you could update and see other things there. But sometimes they'll reset, and we think it's the same ring, but it'll be a lot different in pattern. And for us, it's just sometimes we know, sometimes we kind of look back and can see, but often we're not sure whether is it the same ring. I don't know. It might be. It might be.
Different weights for different behaviors. Repeated behaviors, you start adding, more weights.
Yeah.
Are they difficult to predict from that perspective?
We don't. So we.
For a given group.
Yeah, for a given group, we won't weight the behavior so much as we'll. We use kind of a set of decision trees.
Probability
and
calculations.
Yeah. So we'll use kind of a. Yeah, so we'll use a set. Right now, we've tried various things, but right now it's a bunch of decision trees that are splitting off and deciding what characteristics are strongest at this moment. This is just a visualization of flash fraud. Actually, you could. In the interest of time, I won't go much into this, but the dark green is kind of a 14-day window. Lighter green is a 30-day. And the lightest is a 60-day, and we're using kind of seeing the pattern in those three windows and looking for various patterns that come up. Okay, diversity matters. So what I mean by this is I believe that no singling modeling method is best. It's kind of similar to what I said before, but there's a lot of people like ensembles, and I like ensembles too. But a lot of ensembles, like, for example, random forest, is about doing the same thing over and over again with random or slight variation. I like using diversity, and I'm going to explain what I mean by that. We're using diversity of methods and creating an ensemble, a diverse ensemble, which is what we do. And so, in that diversity, you make hopefully smart, non-random choices, kind of like what I was saying with flash fraud, where you say, this is the kind of thing we need to use here, this is the kind of thing we need to use here, and making conscious decisions about what data to group together and what things to look at together. And that's what I refer to as our fraud ecosystem. So we're making those kind of choices, and we built it into what I call a fraud ecosystem. And this is kind of my way of visualizing kind of the world of signals or features. If each box is kind of a feature, and the arrows are links between them, interactions between them, what we do instead of trying to just have one model that looks at everything at once, and I won't have time to get into why I think this works better too much, but I think it does work better. What we do is we try to group things together. So we'll take this and do a submodel on it. We'll take that and do a submodel on it. And it could be a decision tree, or it could be a neural net, it could be a logistic regression or something else. And and so on. We'll keep grouping things. There's some interactions you'll miss, but I think making smart decisions and grouping your data like that, you could get a lot of value from that. And then use diverse, again, choices that were each one, you're using the choice that's most appropriate for that, or that seems to work best for it.
This looks more like a sequential circuits, sequential machines that we used to do. And is there a sequential parameters involved in it?
You know what? A lot of there's the only sequence is because we do things because of limited resources. So our modeling has kind of evolved over time. So maybe we start with this, and then we figured, hey, let's take a look at this, and we'll go to different, and we'll make some conscious choices that, okay, we're going to take this group of stuff and we'll do that all together later. But it is sequential because, and I'm going to get a little bit into this later, but. Yeah, but not like an automated machine type of sequential. Yeah. Okay, so we do some things that are a little different than kind of the traditional terminology. So I'm going to give you some terms I basically made up. But so we have a lot of things that are a bunch of trees, decision trees, but they don't follow into the structure and technical way that a decision force is constructed. So. And it's often an organized set of trees with a specific way we do them. So I'm calling that a decision grove. And then sometimes we often tend to have an artificial structure on top of a tree. So we'll have a tree and then we'll have something on top of it, or several trees and something on top of it that's artificial. So we'll take the trees, we'll kind of do something beyond that, something man-made, something modeled or done beyond the tree, and created a structure on top of it. And so that's what I'm calling a decision treehouse. And then the last thing is, so we have a bunch of random forests, we have a bunch of groves, we have a bunch of trees, we have tree houses, we have other things like logistic regressions. So that's kind of, what would you call that if you have these kind of things? Well, that's what I'm referring to as an ecosystem, a decision ecosystem. So you have a bunch of kind of diverse things. In a way, it's a kind of ensemble, but that stresses diversity of various types of things. So let me show you what our ecosystem looks like. We have a naive Bayesian classifier, so a top-level model. I'm going to explain why in a minute, in a bit. And that it can make automated decisions, but it basically, I don't show the rules engine there, but it goes through a rules engine and it shows cases to investigators. And then within that naive Bayesian classifier, we have a lot of things feeding in. We have decision trees. We have those things I call tree houses. We have a lot of simple variables as well. We have logistic regressions and those decision groves. And then we have neural nets, random forest. And we have some specialized things that hopefully I'll get into. I'm actually going, oh yeah, I have time. We have some kind of specialized processes, which I'll get into. One is called scope. Another is a link analysis process, which I won't have time to cover, but you could ask me about it later if you'd like to. But basically, it's a multi-step process where we create links, then we prune links, then we have a decision tree at the link level. We have a decision tree at the merchant level with all their links. And yes.
Now you're talking odds and probability, right? So do you have a confidence limit? What kind of probabilistic algorithms do you use, and how do you assign the confidence intervals or limits you want to call?
Yeah.
Without that, probability doesn't mean anything.
Right. So we're building, I guess it depends what we're looking at. At the subcomponent, as we're building the components, we do that. So if we have like a logistic regression, then we're looking at that. If we're doing a decision tree or something else, we will kind of look at we'll do training and test and replication over time and make sure it's consistent and still holds over time. But the other thing, actually, when I get into scope, I'll talk a little bit of how we kind of adjust for sample size and things like that. Okay, so, and then I mentioned the flash fraud group. So basically, the idea is we have a bunch of different things, and we feed that into one. So a lot of things are models in themselves, and they feed into another model. And we actually have several models that are native Bayesian classifiers, but they feed into these larger models, which are basically add up all the components. So that's the ecosystem, just generally what it is. Now, moving on to the next lesson, flexibility matters. So I said I'd talk about why we use a naive Bayesian classifier. If you're familiar with them, it's really a pretty simple algorithm relative to a lot of them. It's basically kind of a scorecard. So it's, and it has, it's been described as surprisingly robust. So it is a good model, but you do lose a little accuracy. One of the reasons we have the naive Bayesian classifier as a top model, I'll explain why a little more in the next slide, is because flexibility matters. And it matters, I think, in lots, for probably what a lot of people do here, but for fraud, for us, it matters a lot. So by flexibility, I mean you can sacrifice some accuracy today to be able to change quickly because things evolve really fast, and you want to be able to move fast, and that's absolutely vital. So so let me just talk about the naive Bayesian classifier and why we use that. So the top level model that adds everything up, it's really there to add things up, and it's less important to our accuracy than how good the pieces of the ecosystem or the submodels that we have that add up to it. You do lose a little accuracy, we found, from using the naive Bayesian classifier, but it's not that much really if you are careful about things like correlation between variables, which is something you have to watch for with this type of model. More important to us is it has some advantages in production. Basically, it allows we have kind of a modular design to our modeling environment. We have a modeling environment, a custom app that's a modeling environment, and it has a modular design in that each of these meta variables we can pull in, pull out. We don't have to kind of redo the whole model at once. As we were talking about before, we've done things sequentially because we kind of figured we have limited resources. We have more things we want to do than we could get done, and we sometimes have to switch gears because we see something emerging in front. We have to address that, or we get a new data source or something, and we can add a variable. One of the nice features of this kind of model is you can just add something, and everything else theoretically should be fine. If you're careful about the correlations, you could just add stuff and pull stuff out, change it. It's kind of like while you're driving, fixing your car, you could pull something out, pull one wheel off, fix that, throw it back on, and then keep on moving. And so that's what I like about it. And as I said, we need to keep moving quickly in fraud. So that's one of the reasons that we like it. Okay, so another lesson, automate what you can. There's lots of things you can automate. You can automate the way you calculate metrics, statistics on kind of how things are going. You can automate some quality control tasks. You get some evaluation tasks of how things are working, some calibration of the models themselves. And that's the example I'm going to give. The scope is really about automatically recalibrating some of our pieces of our models. And scope stands for systematic, categorical, odds, and probability estimation.
On the probability estimation,
Yeah.
what kind of distribution do you normally assume? A statistical distribution, whatever it is.
Yeah.
For this particular application, do you use that? Because probability estimation is based on different
Yeah.
distribution, chi-square distribution, or
Yeah, yeah.
distribution you use.
Yeah, so we're predicting a binary event usually. So we're predicting,
Binary distribution.
yeah, so it's like for fraud, it's
Yeah.
bad,
Yes, sir.
a fraud merchant or not a fraud merchant. And so we'll use, and what we actually use, which I'll just go to now, is what we use is a Bayesian kind of, theoretically Bayesian process. Yeah. Yeah. So we're using theoretically a Bayesian process to do a sample size adjustment for categorical variables. So we have a lot of things, we have a lot of different kinds of things, but one of the things that keeps on coming up is categorical variables where we just have a bunch of categories. Examples are email domains or products we use or foreign country, the risk of certain foreign countries if you see a transaction from it. And so there's just a lot of things that naturally fall into categories that, you're not creating a category, they just are categories. And sometimes when we create categories of ourselves, we can use the same process. But basically, when you create categories, what we have is a process that basically says, it uses kind of Bayesian logic to say what is the best estimate as to the true probability of this category. So you have let's say you have the probability of the population, actually let's make that lower, and then you have this high fraud risk category here. And the high fraud risk category, the actual risk, let's say, could be the category risk, but if you have a really small sample, maybe you just got like 1 out of 1 bad or 1 out of 2 bad, it's really probably closer to here, the baseline population. So basically, we have a kind of formula that'll say, if it's a real high population, it'll be close to here, the risk that it'll assign. If it's a real low, real high sample size, it'll be close to here. If it's a real low sample size, it'll be close to kind of the baseline rate, and it'll be somewhere in between based on this formula. So it creates a sample size adjusted formula, and it recalibrates. So what this process does, besides adjusting for sample size, is it automatically recalibrates every day. So all these categories, we have a rolling risk assessment every day that's up to date of these categorical variables. And we have done some enhancements to it. We've kind of, because we have these fraud bursts with specific things, we have kind of a short-term assessment, a long-term assessment for the category, and we could using some logic, pick which one's better. We have some other hybrid kind of categories we've created. We've created a decay curve and fuzzy logic to change how we weight things over time, which actually I'm going to cover that in a minute. Let's see. Okay, so now this one might be kind of one of the more controversial points because I think a lot of people who do modeling like Blackbox methods. I've become wary of black boxes. And so black box methods, there's ways to extract information out of them, but generally things like random forests and neural nets or deep learning tend to be black box-ish. And I'm not saying never use them. I'm saying that only use a black box if there's a big benefit from it. And sometimes there is. But the reason I say that is because my experience is that when you use white box methods, the first time we do a white box method, we often encounter something that surprises us. Something that says, wait a second, something's wrong here, and then we research and figure it out. If you had a black box, it's something we would never know. It's something you would never know was an issue, and so you just trust it, and it seems to work, but you don't know what your problems are unless you can kind of see them sometimes. And it could be lots of things. It could be data problems, just basic problems with the data, which we encounter quite often. The data could be fine yesterday and bad today. Something could have changed, and that happens to us. There could be timing or cause-effect problems. So for us in our business, I think it's true in a lot of cases, but timing is everything. For example, with fraud, we eventually catch all fraud. It's just a question of will they take us for a lot of money first? Because if they take us for enough money, they become obvious, right? So we eventually catch all fraud. It's a question of how soon you catch it. So timing is everything. And so, and there can be timing issues, even though we build our kind of model training testing to control for timing and evaluate things based on looking at things now and then looking at outcomes later. There's odd things in the data that can happen that can make you think things happen one way, but cause effect could be reversed. we've encountered that a few times. Again, I don't want to, if you want to ask me about that later, I'd be happy to go into it if we have time for examples of that. So there can be, even when you use kind of good methodology, you could have obvious overmining, or you could have an algorithm that really is exploiting an anomaly. When you look at it, it's clearly exploiting some anomaly. Like for example, it could be something that you knew something funny was going on with one product or process or something at a particular time, and it's associating that with something bad, but it really is not applicable anymore, or something like that. You could have situations like that occur. You could have things you just don't want in the model. So an example of this would be, you could have a model that is discriminating for reasons that you didn't intend it to and that are illegal. You don't want that to happen. So you got to be careful, to make sure you understand why it's doing what it's doing. And there can be, for us, because we use that naive Bayesian classifier, we got to watch for correlations. And even if you know the surface variables are not correlated, you can end up with correlations you didn't expect. Because the machine learning can sometimes, or like a decision tree, for example, could trick you, or a neural net can trick you in the sense that you'll think it's doing one thing because that's what you put into the model, and it'll actually be doing something else. And I could give you a quick example of that. So again, with a naive Bayesian classifier, you want to have kind of uncorrelated things, or it's robust to that, but not really highly correlated. So we have like age, and it's a bunch of things related to age in one place, and let's say certain types, swipe versus keyed transactions, the more somebody's keying their transactions, greater the risk they are in kind of card usage generally. So a funny thing is that, so if we're looking at kind of things, a bunch of things related to keyed and swipe, one thing that came out of decision tree, for example, is that, okay, between 50% and less than 100%, so above 50%, less than 100% swiped or keyed is less risky than exactly like let's say 50% keyed. Well, it's actually not having to do with being keyed. It has to do with the fact that between 50 and 100%, you have to have at least 3 transactions, because it's a count of transactions. So you have to have, so it's basically, even though we have age somewhere else, it's indirectly doing a proxy for age by using a percentage in there of keyed percent. And so it's much more risky if somebody has like 1 transaction with us than it is if they have 5 or 10 or so on. So that's just an example of how you could have unexpected effects from the machine learning algorithms. Settling for 80% of value. What I mean here is, okay, if you like, let's say you're working with some new piece of a new feature or new concept, and you think you could get it better and better, you should probably stop when you got it 80% right, because it's just kind of at a certain point you get diminishing returns, and it sounds maybe obvious, but it's one of those things that's hard in practice for a lot of people to do, because especially working with data scientists, they'll be curious, they'll be interested, they'll want to keep on going and getting things better and better, right? If you're faced with a problem, you want to get it as good as possible. But you should probably stop at 80% and move on, because if your situation is anything like mine, there's lots of things to work on, and your value is probably higher spent on working on something else and adding value on something else. Couple exceptions is if you have no human resource constraints, or if you've run out of things to do, and if you're in those situations, I probably want to meet you, because I haven't been there. So last thing in terms of lessons, and I think there's one other slide after that. Deliver what your customers or users want, and figure out what they want and deliver that. So some examples of things that we found our users are really interested in is reasons for the score. So we tried to get better and better at giving them some insight into the model and why this particular customer looks risky, and they'll start their investigation for there, and it adds a lot of value to them. Score stability, this one's I haven't really heard about, but we found is real important. So when we were first building the models, there's a lot of tendency to want to use kind of like time windows, and we still do that sometimes. Like, we're looking for this thing in the last 30 days, or measuring this percentage in the last 30 days, 60 days, 7 days, or something. That's fine, but one problem with that is that you get some score instability from that. So something has a 30-day window, and it goes down to day 31, and let's say some big transaction or some weird thing happened. It goes to day 31, all of a sudden the score has a big shift in one direction or another. And that, we've gotten these questions from our users that say, why did the score change? What happened? And really, kind of the explanation is an artifact of the way we model. It's not a true risk change, right? When you went from day 30 to day 31, there wasn't really a big change in that person's risk. It was just kind of the way the models work. So we try to find ways to get around that. And one thing we've done is kind of, instead of using kind of a firm cutoff, use kind of fuzzy logic or discounting over time to change the weight of something rather than kind of just a window. Another thing we're doing is found in at least one of our models that actually, instead of today's score, the best measure of risk is actually a time discounted, where each prior day is worth less, weighted less. Kind of a time series of scores is actually more accurate than today's score, and more stable, of course. So that's another thing we found is useful. Another thing is feedback, adding feedback to the model. I don't just mean that people come to us and they say, hey, can you do this? That's important too, but the one thing that we've done is we've had feedback integrated into kind of their user interface, where they can actually give a thumbs up or thumbs down to something they see at the variable level for a specific merchant, and give us feedback on what they're seeing and what they think. So one last thing I just wanted, so we've done a lot of things, we've come a long way, and here's kind of some of the results. We've reduced fraud losses by like 80% in the last several years. At the same time, the cases that have to be looked at by people have gone down more than in half. And the portion of fraud we catch now, most of our fraud, first the merchant goes to underwriting. The ones that get through underwriting and actually become our merchants, most of them we catch before they process their first batch, which was definitely not the case before. So we've done a lot of major improvements, and of course it's still a journey, and there's lots of things we continue to try to improve on. And these improvements were not just due to the models and decision sciences group, but they're due to others as well. Credit card and check ACH transactions, we do both. Check, so like a check. ACH is just an electron. Most checks now are not actually paper checks. They're just like ACH transfers from one bank to another. So you write a check, and actually used to be the check would go to the Federal Reserve. Now it turns into just like a transfer from bank account to bank account, which you can do directly, a bank-to-bank transfer. So that's the other kind of major transaction we have. So for example, since we do payments in QuickBooks, somebody can send an invoice to somebody in QuickBooks. They can put, the receiver of the invoice can put their bank account number in there, and then through us, we'll process the payment from one bank account to the merchant's bank account, from the customer to the merchant's bank account.